Let's go over activity 11. So for question 1, we're going to load up the Cust Loyalty dataset. And in the Cust Loyalty dataset, we're interested in trying to develop a model that describes how a customer lifetime value, customer LV, may be related to these other predictors here, the gender of the person, marital status, total transactions the person made at the company, etc. Part A asks us, if we were to use the all possible models technique, how many models would be considered if we excluded and included interactions into the model. So what we know is that it depends on the number of predictor variables that we have in the data, k, and the only thing we need to do is figure out the effective number. Now, normally this would just be the number of variables if each one was just a numerical predictor, but we know that when we have a categorical variable with more than 2 levels, that needs to be represented by a set of indicator variables. So we see here that all of the variables are numerical. Gender, married are just categorical with 2 levels, so they can be represented by a single indicator variable. But income has 6 levels, and so needs 5 indicator variables to represent it. So k in this case would be that 5 for income here, and then just one variable for the others. 1, 2, 3, 4, 5, 6, 7 total. So k would be equal to 12 in this case. So if we ignored interactions when doing the all possible procedures, we would have 2 raised to the k power number of models, which works out to be a little over 4,000. And if we included all two-way interactions, we'd have 2 raised to the k times k plus 1 over 2 models, which works out to be like 3 times 10 to the 23rd power. No possible way to actually go through all of those. So k is the number of effective predictors in the model, which is equal to the number of numerical predictors plus the number of categorical variables with 2 levels plus the number of indicator variables required to represent categorical variables with more than 2 levels. All right, so part B asks us to do the all possible approach, but considering only a maximum of 10 variables in a particular model and not to consider any interactions. So what I'm going to do is I'm going to name the result all here, and the syntax here is just reg subsets. And what we do is we put in the formula of the most complex model we're interested in considering. Now in this case it is just the full model with all predictors in it, but no interactions, so customer twiddle dot data equals to cust loyalty. And we can add in the nvmax argument to say, all right, put a cap on the number of predictors that we want to consider at 10 here. Now one thing to remember is that since reg subsets does not respect model hierarchy, it will sometimes leave out indicator variables that represent particular levels of a categorical variable. The net effect is to combine those with the reference level. So we can fit the all possible regressions, and then we can run cmodels to see some of the best, the models within 4 AIC of the absolute lowest value. So I'll resize this for a second. So how many predictors are in the model with the lowest AIC? Well, it says that there's 8 different predictors here. Notice that we have a few of the indicator variables representing income, but not all of them. And B2 follows up on that. Only certain indicator variables representing income appear in the model with the lowest AIC. In effect, what 3 levels of income are being combined together to form the reference level. So one thing that we know is that if we leave out an indicator variable representing a level, then the model is going to treat that level as the same as the reference level. It essentially combines those. And so in this case, since income has 6 levels, the first one, the reference level, is F0 to 30, so $30,000 or less, 30 to 45,000, 45 to 60,000, etc. It's left out the 0 to 30, 30 to 45, and 45 to 60 levels here. So they're combining them all into one, essentially. So it is combining the F0 to 30 reference level with F3245 and F45-60. So in effect, really, the reference level, and I'll put that in quotes, the effective reference level here is basically an income of 60,000 or less, since these three levels are being treated together. All right, what variables do not appear at all in the model with the lowest AIC? Well, we see gender does. Does marital status? No, it does not. So married does not. Income does. First purchase? Yep. Loyalty card? Nope. Wallet share? Yes. Total transactions? Last transaction? Yes. All right. B4 says that there are two other models in the output of C models. We see them here. And their AICs are really not that much higher. We've talked about that when we have models whose AICs differ by within 2, then there's no compelling reason to really choose one versus the other, so we can either choose the simplest or maybe one that's easier to interpret here. So would we recommend either of these other two models to our boss? Well, no, they're more complicated because they have more variables here. If the boss insisted on using one of these other models, would we object to the decision on statistical grounds? Well, no, not really. So the difference between model number 1 and model number 2, the AIC is only 1.4, and that's negligible. There's no compelling reason, really, from a statistical point of view, to choose one versus the other. And the very lowest versus in third place here is a difference of about 2.8. So we're still talking roughly 2 here. So if your boss insisted on choosing one of these models, then that would be fine. So we would not recommend choosing either of the other two models because they are more complex. They have more variables in it. However, if the boss insisted on using one, you would not have a compelling statistical reason to not go with his wants, desires. Their AICs are within roughly 2 of the absolute lowest. Okay, Part C says that given enough time and patience, it is possible to form the all-possible approach while considering the two-way interactions. It's just a lot of models as long as we put a hard cap on the number of variables that we consider. So an alternative is to perform a search, basically propose a model and then augment it in steps. At each step, either add in a variable that's not already in there or kick out something that's already in there that may not be important. So the way that we do this is to start out by fitting the simplest and most complex model that we want to consider. And typically that's the naive model and the full model. The naive model we can fit as just the Y variable, customer lifetime value, twiddle 1 in the cus loyalty dataset. And the full model, in this case, we want to fit all two-way interactions between all the variables. So that would be customer LV twiddle dot squared. Data equals cus loyalty. All right, so we're going to run the step procedure, which is the command step. The first argument is the model that we want to start out with, so basically start out with nothing in the model. The scope argument, you're never really going to change. It's always going to look like this, assuming you've defined your simplest and most complex model as naive and full. It's just defining the scope. The simplest and most complex models to consider. Direction equals both. You'll never change unless you're pressed for time. Both says to consider both additions and deletions of variables to and from the model. And trace is equal to 0 turns off the narrative, basically. It turns off the model building procedure and steps so that you can't see it, but it still saves the result. So trace is equal to 1 is what we're actually going to have here. Because we do want to see the output, trace is equal to 0, we'll just hide that output here. So let's run. A lot of outputs to the screen here. All right, so the formula presented in the very last step of the output actually gives the order in which the variables were added to the model here. So which was the first variable added and which one was the last? Well, tote transactions was the first, while the interaction, wallet share, last transaction was the last. Is the model found with the search using STEP preferable to the model found using the exhaustive enumeration, reg subsets, going through all possible ways we could build this model? All right, well, we'll compare the AICs of these two models, and it looks like the AIC of the model found in the search is this. So the AIC of the model found via the search is 5185. That number in particular doesn't tell us all that anything interesting. It's only when we compare the AICs of the models those numbers really mean much. So let's scroll up. And it looked like the AIC of the best model found with reg subsets is substantially higher. So the model found with STEP and considering all two-way interactions is substantially better, definitely closer to the truth than the one found without considering interactions. So once again, we see that interactions are playing a pretty important role when helping define these relationships, and you would do your model injustice if you were to ignore them. So would we insist on using this model instead of the one from reg subsets, even if the boss strongly preferred the model without interactions? Well, we really wouldn't allow our boss to choose that model. So yes, we would insist on using this model, even though it's a lot more complex here, because a difference of AIC of, in this case, it looks to be about 140, is extremely massive. Remember, any difference that's at least 10 is very, very strong evidence that the model with the lower AIC is, in some sense, better, closer to the truth, and a difference of 140 is just ridiculously big. All right, so C3 says that interpretation of models with interactions is difficult, so not a big surprise your boss may not want to go with that model, but in this case, there are compelling reasons to go with the model with interactions. So to really talk about the model, we either need to write out those implicit regression equations, and that's not very fun, or we can look at interaction plots. So the C interactions command will break down all the interactions in the model and let us visualize what the relationships look like. So let's go ahead and run C interactions on the result of running step. S, the result of running step, is that final model that's chosen, the one that's found at the end of that procedure there. So we're asked to describe the relationship between the lifetime value of the customer and income. And in this case, it has an interaction with wallet share. So let's figure out what this relationship looks like. All right, well, that's wallet share total transactions. That's wallet share and income. All right, so this is what we want to talk about. We're describing the relationship between customer lifetime value and income. And we're asked which level of income has the highest lifetime value. And the answer actually depends on the individual's wallet share. So what we see is that for casual customers, wallet share near zero. Wallet share is a measure of the fraction of that customer's purchases that they actually make at that store for similar types of products. So a customer who shops at Food City, Kroger, Ingles, etc. for their grocery needs, their wallet share for, say, Kroger may only be 10% if they do 10% of their grocery shopping at Kroger there. So for casual shoppers, it looks like that the high-income customers actually have the lowest lifetime value. And for very loyal customers, ones that are using that store for the majority of those sort of purchases, it looks like that the high-income customers are by far the ones that have the highest lifetime value. So, kind of some interesting actionable insight. You might think that, okay, individuals with higher incomes probably are worth more to the store overall because they have more potential to be spending money. But it looks like that's not quite the story the model is actually saying. It says that, okay, the income of the individual does seem to matter quite a bit, but the interaction of income and wallet share plays a pretty important role. If you're talking about customers that every now and then shop at the store, have pretty small values of wallet share, well, actually, it turns out that the customers with the lower incomes tend to spend more over the course of their lifetime. Now, the story reverses if you're looking at more loyal customers. The customers with the higher incomes have a much higher lifetime value. And in fact, for those high income customers, it looks like the relationship between customer lifetime value and wallet share is positive, while for all other levels of income, it's negative. So for high income customers, the relationship between customer lifetime value and wallet share is positive, while for all other levels of income, the relationship is negative. Now, I don't feel like that makes the most sense. You would think that, customers with higher values of wallet share that are more loyal probably would be spending more and more and more until their lifetime value would be bigger. But maybe this company isn't really doing marketing and promotion all that great, and they're spending proportionately way too much on those customers that do seem to have large values of wallet share. They're spending more than really what those customers are bringing in. And so maybe there's a marketing advertising mismatch here. All right, part C4 says that the model selected in a building procedure, the one we're choosing that looks to be closest to the truth, losing the least amount of information about reality, the one with the lowest AIC here, still may not actually give us a reasonable reflection of reality, because nowhere in the AIC is a check to see if the assumptions of the regression model hold up. So let's get rid of this. And let's actually look at check regression here just to see, all right, is this model a reasonable reflection of reality? Looking at the p-values of the test, no big deal. We fail the test for equal spread, normality. We fail the test for linearity and wallet share and total transactions. But we have a pretty big sample size, so we're not too surprised we failed. So, all right. What do the residuals plots let us know? Well, the residuals plots aren't all that bad. We see the pretty standard small bending away from the diagonal line in the QQ plot, indicating that the distribution of the residuals as a whole is roughly normal. We don't see any overall global curvature in the band of residuals, either up or down, so the overall linearity of the model seems to be appropriate. The only thing that may be a little troublesome is the presence of these outliers. We may have some heteroscedasticity. It looks like at the very lowest predicted customer lifetime values, the typical size of the residual is maybe only about plus or minus 100, and it may be a little bit bigger once we start predicting values of about 500 or so, and maybe it gets a little bit bigger to the right of there. So the equal spread assumption is questionable here. The typical size of the residual looks to be getting a little bigger at larger predicted values. So maybe that's an issue for the model, but it's not a huge effect. If we were to delete a few of these points up at the top and the bottom, then roughly it would look about the same everywhere that we look, the vertical spread in the thickness of the residuals band. So I'd probably be comfortable using this model, but it definitely has some minor issues. All right, part D now asks us to consider predictive models. The best predictive model very often is different than the best descriptive model because the two models have different goals. The descriptive model is trying to lose the least amount of information about reality, so we try to minimize the AIC. The best predictive model is the one that's making the best predictions on genuinely new data. So to evaluate a predictive model, we actually need to start out by taking our original data set and splitting into two chunks: the training set, where all the model selection happens, and then the holdout sample that we use as a sanity check. We actually use our final model to make predictions on the holdout sample to make sure that it really is generalizing well to new data. So, all right. So the first thing we need to do is to split our original data into the training set and into the holdout sample. And the code has been provided for you already. I'm just going to remove this little thing from the art chunk. We basically prime the random number seed so that we can reproduce the results if necessary. If we didn't do this, then if we were to rerun this line of commands, we get a different training and holdout sample. So set seed 320. Train.rows, this command chooses at random the rows from the custom loyalty data set to put into the training set and then into the holdout sample as well. All right, so same sort of strategy. We're going to fit a whole bunch of different models on the training data and estimate their generalization errors, and then kind of cross our fingers and pick one that we think might do well on new data here. So the way that we do this is to use the command build.model. Now, build.model uses as its first argument the formula of the most complex model that you want to consider. Now, in this case, since we've already built up a pretty decent model on the descriptive analytics side of things, then we can go ahead and just use this as the most complex formula here. So you can actually extract the formula from a particular regression model by typing in formula and the name of that model here. And so here we have some individual predictors, we have some interactions, and so let's run build model going all the way up to this model here as the most complex one. So what I will do is I'll save the results of build model to BM here. Instead of actually typing out that formula, I'm just going to leave that as formula S. R will figure out that that's the formula that I want. I'm going to make sure to build this on the training data. Make sure data equals train is always going to be what you're putting in to the build model function. Seed equals 320 because it's estimating the generalization error with repeated k-fold cross-validation. It's a random procedure. You want to be able to reproduce the results and set the random number seed along with the argument here. And then prompt equals false is important for knitting. Basically, if you are asking it to fit a lot of models, it will spit out a warning that says, hey, are you really sure you want to do this? It might take a really long time. And if you say yes, and it keeps going, you might actually have to force quit RStudio to actually do anything else. So in this case, I've made sure it doesn't take too long. So we can just run the build model command. So it'll be going through a few hundred, if not a few thousand different models, estimating their coefficients on the training data, and then estimating the generalization error using repeated k-fold cross-validation. And at the end of the day, what we get is a table of the estimated generalization errors of the best model found with 0, 1, 2, 3, etc. predictors, the estimate of that generalization error, and then a plot of these same results. So the points represent the average estimated generalization error found with that repeated k-fold cross-validation. And since by default it does it with 10 repeats, there are actually 10 different estimates of that generalization error, and so these error bars give an idea for how spread out those different estimates were. Okay, so part D1, how many predictors are in the model with the lowest estimated generalization error? Well, that's given to us by the blue star over here. It looks like it's 14 variables, and we can confirm that over here. So we have 14 variables. Do we see any obvious signs of the model becoming overfit when too many variables are added? So overfitting is the biggest concern with predictive modeling. We don't want to make our model so complex that it's memorizing the quirks and characteristics that are particular to that set of training data that we have. And so very often if we do make the model too complex, then it actually starts predicting worse on new data than if we had stuck with a simpler model. And so we see a tiniest bit of hint of that, where we see the generalization error of these models getting smaller as we make them more complex, and then maybe a little bit of getting larger as we increase the number of variables to that model. So my best response here is maybe. There is a slight hint of an uptick in the estimated generalization error after 14 variables are added, but it's not huge. So we may do a little bit worse by including too many variables, but we definitely like to err on the side of caution and go with a simpler model if we can get away with it. All right, so let's see what model actually ends up, performing the best on our holdout sample. So our two reasonable choices are either the model with the overall lowest estimated generalization error or the model selected with the one standard deviation rule. Basically, it says, all right, any two models whose estimated generalization errors are within one standard deviation of each other, basically the size of the error bar, are more or less equivalent in terms of predictive performance. So we can get away with a simpler model, then we can sometimes do that. So this dotted line right here is drawn one standard deviation above the lowest estimated generalization error, and so the simplest model, whose error is below that line, is the one selected with that one standard deviation rule. All right, so we have a bunch of models for us to run, and the command that we can actually check to see what the actual error is on that holdout sample is called generalization.error, specifying the name of the model and the name of our holdout sample. So if we use no model whatsoever, the typical error on the holdout sample is $819. So that's basically our baseline. Our models better beat that by quite a bit, otherwise what's the point of doing modeling? All right, if we had straight up just predicted customer lifetime value from all the predictors, no interactions, estimating the coefficients on the training data, making predictions on the holdout sample, our error would have been $170. So huge improvement over the naive model. There's definitely information in this data set about customer lifetime value. What if we had used the full model with all two-way interactions, estimated the coefficient on the training data? How well would this have done? Well, actually a little bit worse. So the typical error on the holdout sample is about $175, about $5 higher than had we just done the model with the predictors themselves, with no two-way interactions. Most likely, this model with all two-way interactions is overfit. It's probably memorizing some of the quirks that are unique to this particular set of training data that aren't present in the holdout sample. And so it's actually making slightly worse predictions. Well, what about the formula found with the AIC search? Well, we can fit that model and we can look to see how well it does. And there we go, way better than either of those two models. So doing no sort of search, no sort of model tweaking, either just, let's predict y from all the variables or from all the variables in all two-way interactions. We had errors of about 170, 175. Doing a little bit of effort trying to search for a model that gets closest to the truth, we actually have an error on the holdout sample of only about $150, so significantly better. Now, those models aren't designed to make good predictions, just usually kind of makes sense if you end up with a model that is closer to the truth, it probably will be predicting better on new data. But let's see how well the models found by build model actually do. So in this case, the formulas are hard enough that I don't actually have you fit them. But instead, I just say, all right, the one with the lowest estimated generalization error has a typical error of 166 or 148, and the one with the one standard deviation rule is at 166. So in this case, the model with the overall lowest estimated generalization error is actually the one that we found with the AIC search here when we were looking for a descriptive model. But not by much, 148 versus 147.6, about the same here. So model found via search procedure when doing descriptive analytics has a slightly lower error on the holdout sample than the model found with build model the lowest estimated generalization error, but not by much. So 147.6 versus 148.4 here. So the predictive model building procedure did not end up being the winner, but it's a very, very close second place. And who knows, with a different set of holdout data, that predictive model might have done even a little bit better than the one that we found during the descriptive search.